All right, so 2010 says, I guess I can just show it to you. It's kind of this crazy thing, and again, we looked at some of these in class, where it's cosine minus 1 over x squared. So you write cosine, you subtract 1, and then you divide everything by x squared. It reduces all their powers. And then it does define this when x is non-zero. So it's pretty much just telling you that's the original y value. And then in the problem, it's like this g. Well, g is 1 plus then the integral of this. So you're going to make some substitutions, subtract. You're going to have to integrate some things. We'll kind of just go through this. And at the end, it's an alternating error one again. So I like 2010. It's really a fair question. Feel free to pause right now and take a screenshot of that if you don't have it in front of you, because I'm going to have to move it up to kind of go through the problem. Okay, so first part of the problem, it says write the first three non-zero terms and the general term for cosine x. Okay, and it's just telling you to do that because it knows you're going to use it for the future one. Okay, since I know I'm going to subtract 1, I'm going to go ahead and write out 4 terms because I know that I'm going to lose one of the terms when I subtract. Okay, so there's cosine. As a reminder, it's an alternating x to the 2n over 2n factorial, if you want to look at that. Okay, so there is, oh, I guess it just said the first 3 non-zeros, so I shouldn't have wrote that, but that's kind of silly because I'm going to need that later on. And then I'm going to use this to write out f. Okay, so f, it does tell us that the y value is -1/2, and then we're going to write cosine minus 1 all over x squared. So all that's going to do is if you take this entire thing, which is cosine, and you subtract 1, you're just going to delete the 1. And then if you divide all the remaining terms by x squared, okay, you're going to get that -1/2 that you already got right here. Okay, and again, that's kind of an obvious thing. We just can't let x be 0. So we're going to get this divided by x squared. It gives us the -1/2. This divided by x squared is going to be plus x squared over 4 factorial minus x to the 4th over 6 factorial plus ... It's still an alternating series. X to the 2n minus 2 over 2n factorial, where this whole thing then starts at an n value of 1. So this corresponds right here to n equals to 1, n equals to 2, n equals to 3, and so on. Okay, so we wrote out the first 3 non-zero terms in the general term for cosine x right here. And then f was this silly function where it's like cosine minus 1. Subtracting 1 from this polynomial canceled that. Dividing by x squared gave us all that. We can remind ourselves that we knew they actually defined the original function -1/2, and that is what we got. Okay, part B. Part B is actually a really easy question. It says, use the Taylor series for f found in part A, this guy, and decide whether or not f has a relative max, a relative min, or neither at x equals 0, and give us a reason. So look at this thing. If we just look at kind of the first 2 terms, right? What does it look like? A -1/2 plus an x squared. Doesn't that look like something like this? It looks like a quadratic that's smiling up because it's a positive x squared. And so really what they want you to show here is the second derivative test. So the second derivative test says this. The second derivative test. We know that f prime of 0 is 0, and we know that f double prime of 0 is positive. Okay, and how do we know that? Well, first of all, there's no linear term here, which means that the first derivative has to equal 0. The second derivative is 1, right? Or no, actually, it's positive. It's not actually 1. If we take 2 derivatives, we're going to get it to be 1/12. Either way, it's positive, right? The second derivative term is positive. The second derivative is positive, which means it's concave up, and it's got a horizontal tangent, which must mean it's a relative min. Okay? And again, that is the second derivative test. They love using Taylor series. They kind of go back and answer questions about things you've already known in the past. Again, you probably maybe want to go through and show that the second derivative is not just greater than 0. Maybe you want to actually say that the second derivative of 0 is 1/12. And how do I get that? Again, just take the derivative of x squared, and 4 factorial is 24. So if you take two derivatives of that, one derivative is going to get you 1/12 x, and then another derivative will give you that 1/12. Okay? Okay, part C, write the fifth degree Taylor polynomial for g. Well, g they define as 1 plus the integral from 0 to x of f of t dt. Now, don't worry about these letters. They just have to use different letters here than they do here. They could have put x's here and t's there, but they just switch it up. Okay, so all we're going to do is go at our function here and write the fifth degree polynomial. Now remember, if you take an integral that's got x to the fourth and you integrate it, you're going to get the fifth. Don't worry about the general term. So just integrate. So g of x is going to equal 1 plus, and the integral of this guy is negative 1/2 x plus x cubed over 3 times 4 factorial minus x to the fifth over 5 times 6 factorial. Okay, that's the fifth degree polynomial for g, and I knew 1, and then I just integrated to get f. Again, they told us what to do. G is equal to 1 plus the integral of f. There's f. Okay, now there's g. Okay, that was easy. And then part D is asking about error. Okay, I'll bring this down here again. D says the Taylor series for g evaluated at x equals 1 is an alternating series with individual terms that decrease in absolute value. Alternating series. So that means that the error is just the next term that you don't use. Okay? And so use the third degree Taylor polynomial to estimate the value of g of 1. Okay, so they want us to use the third degree. So they want us to use this. That's the third degree polynomial to estimate g of 1. So g of 1 is approximately plugging 1 into here. Again, that's 1 minus 1/2 plus, what is that? 24/72, 1 over 72. So 1 minus 1/2 is 1/2. 1/2 is 36. 72's plus 1 over 3 is 37 over 72, right? Now adding certain fractions. Okay, and then explain why this estimate differs from the actual value. Again, differs from the actual value. That's them talking about the error. So they're saying, hey, show me that the error is less than this. And remember, if it's an alternating series, then the error is the next term. So this represents the next term. So we know that the error is less than this. This, when x is 1, is just 1 over 5 times 6 factorial. And again, it says, explain why this estimate, the error, is less than 1 of this. Well, we just said that the Taylor series says that the error has to be less than that. Again, 1 over 5 times 6 factorial is certainly less than 1 over 6 factorial. And again, we've shown that if we use the third degree polynomial, the next term is the error. The error is less than this, and we wanted to show that the error is less than this. Check. We got it. Again, go through this problem. Write the first 3 non-zero terms for cosine. Not bad. Use this series to actually write what f is. F is cosine minus 1 over x squared. So I took cosine, subtracted 1, divided all the remaining terms by x squared to give me this guy. The general term, again, just take away 2 from this and offset those things. Write the fifth degree Taylor polynomial. Okay, that's integrating this using initial value. And they threw in some maximum and minimum stuff. Remember, the second derivative test says this. The first derivative test is when you use the sign chart, right? And you say something about, this is y prime, and this is negative, and this is positive. But we don't have information about the derivative before and afterwards. In this case, we use the second derivative test because we know at that point, we know that the first derivative is 0, making a horizontal tangent. And we know the second derivative is positive because we can look at the degree 2 term. And then we know it's concave up, and that tells us it was a minimum. And then we can find error, and we can find an approximation. Again, they said use the third degree, so use that guy, and then that's your error. plug in 1 here to find an approximation for g of 1, and then plug in 1 here to find an upper bound for the error. And all we needed to show with the upper bound, this guy, was less than what they said. Okay, that's 2010.